Magnetic dipole placed in a uniform magnetic field. Magnetic dipole placed in uniform magnetic field. Let us consider a uniform magnetic field like this. This is B, and its vector is I cap. Now we have kept the north pole and south pole like this. That is a magnetic dipole in a uniform magnetic field. And this is theta, south pole, north pole. You know the distance between them is 2L. So NS is the magnetic dipole, 2L the distance between north and south pole of the dipole. Theta is the angle between the dipole moment and the B. Magnetic field. You know, there will be a torque, that is twist, in this direction. So it is Q M B vector along the I cap, that is positive x-axis. Similarly, here QM B vector, that is the force experienced by the south pole. So this is of minus I cap. Now let us consider a dipole of length 2L placed in a uniform magnetic field B. Theta is the angle between the magnetic field and the dipole. Here the force experienced by north pole of the dipole is given by what is QM, pole strength, into magnetic field vector towards I cap, that is positive x direction. And the force experienced by south pole is QM B vector, but that is in the minus direction, that is in the left. So minus I cap. Therefore, F net is equal to Fn plus Fs. So on adding this, it becomes a 0 because they are equal and opposite. So it is 0. Hence, the force will form, these forces form a couple. Form a couple which will rotate the dipole. So that results the torque. twisting force. So this torque, that is tau, is equal to the modulus of vector. The modulus of F vector, force vector means magnitude, into, that is cross product, perpendicular distance. Perpendicular distance between the forces. It is the perpendicular distance between the forces. It means it is, for example, here let me call it T. So this is the perpendicular distance. Do you understand this? So NT. NT is the perpendicular distance between the two forces. Therefore, QB into tau is equal to, what is the force? QB into M. QM into B. QM is pole strength, B is the magnetic field, cross, and then NT. NT is the perpendicular distance. So it means QMB, QMB, and this NT, listen to me, this is 2L, and this is NT. Now what is sine theta? NT by 2L. Therefore, NT is equal to 2L sine theta. Do you understand this? Yeah. So NT is equal to 2L sine theta. So this Q into 2L, what is that? Magnetic moment, dipole moment. So magnetic dipole moment is Qm into 2L. Therefore, we can replace this as M vector cross product because it is the sine theta. So you can remove that. You are able to get B sine theta, means B vector. Because we know A vector into cross B vector is equal to, what is that? Modulus of vector A, modulus of vector B into sine theta into n cap. So based on that, we can arrive at as what? The tau vector as a cross product. Okay. So the tau vector is nothing but the cross product of dipole moment vector and the magnetic field vector. So this is a very important equation. Now let us work out the time period. Time period of oscillations. Time period of oscillations of a dipole placed in magnetic field, uniform magnetic field. Uniform magnetic field is given by T is equal to 2 pi into the whole square root of I divided by MB. So this is the time of oscillation of the dipole. For example, when you keep like this, it will oscillate like this. So we are talking about this time period of this oscillation when it is kept in a magnetic field which is available uniformly. So this is called the time period where I is moment of inertia. It's not correct. Moment of inertia. You know what is I? That is equal to mk square. Okay. What is this k? The radius of gyration. Check down. M is the total mass. So I is equal to what? Moment of inertia. M is equal to what? What is M? Dipole moment. P, magnetic field. This is 2 pi and this is time period. Now let us proceed with the next one. Potential energy of magnetic dipole. Potential energy of a magnetic dipole. Potential energy of a magnetic dipole placed in uniform magnetic field. So previously we discussed about the torque, the twisting force. Then we discussed about the time period. Now we are discussing the potential energy. So this potential energy is represented as U, which is nothing but the work done when it is stored as potential energy. Okay, so this is the work done that is stored as potential energy. What is work done? Force into some displacement. Okay, take down. Now we are working on that. Let us consider the same electric field, not electric field, magnetic field of uniform magnetic field. So here I have kept the what? The north pole and the south pole, a dipole separated by the smallest distance, that is 2L, and the theta is the angle between them, between the dipole and the magnetic field line. And here the force is due to south pole, and this one is the force due to north pole. They are equal and opposite. That is why twist takes place, that is turning, that is twisting force. Now naturally there is a tau, that is twisting force torque acting on it, and we know that value, that is tau is equal to mb sine theta, because you already know tau vector is equal to m vector into b vector. I expanded this. What is m? Dipole moment. What is b? Magnetic field strength. And what about theta? The angle between the dipole and the magnetic field line. Now let me consider a small angle. The small angle or angular element is considered as d theta, the small twist. Now, for which you have got the dw, the small work is equal to, you know already, force into displacement. Here we are talking about the angular displacement. So f d theta. Okay. So this, and instead of a force, you can put the twisting force, torque. So torque into d theta. Do you understand this? The same equation, but in the form of torque. So tau into d theta. And the tau is mv sine theta, then into d theta, and you got dW. That is the small work. Now let us integrate between the limits. MB is constant. You can take outside the bracket and put integral here. Sine theta d theta. So the theta initially there will be some angle, and after that there will be final angle theta f. Initial angle, final angle theta f. That is equal to dw integral is w and mb into, you know very well, sine theta integration minus cos theta. So cos theta and the limits between theta I, theta f, right? So it means mb into minus cos theta f minus of what? Minus cos theta I. Okay. So it means mb is equal to, I'm sorry, w is equal to mb into minus or minus plus. So cos theta minus cos theta I minus cos theta f. Okay. So this is nothing but the work done, and that is also the potential energy, right? Therefore, potential energy due to the magnetic dipole placed in uniform magnetic field is given by U is equal to mb into cos theta I initial minus cos theta f. Now let us analyze the cases. When theta I is equal to 90 degree and theta f final is equal to 0 degree. Now what is U? mb cos 90 minus cos 0 degree. Okay. So it means mb into cos 90 how much? 0 minus and cos 0 1. Is it not? So you can put 1. It means U is equal to minus mb. Okay. Now, if it is not a theta, let me put instead of 0, I'll put theta. In that case, you have to put theta. So here you have to put theta, right? So therefore, minus cos theta. It means minus mb cos theta. It means U is equal to, that is, minus ab cos theta, which is nothing but scalar product. So m vector dot b vector. So I have converted this into scalar product. So U is equal to minus m vector dot b vector. Now you can find, in the case of tau, it is a cross product. Okay, tau vector is equal to m vector cross b vector, whereas its potential energy is minus m vector dot b vector. It means this is the dot product and this is the cross product. Okay. For a magnetic dipole to be in equilibrium, For a magnetic dipole to be in equilibrium. What about the net force? The net force is zero, right? Therefore, the net torque will also be zero. It means theta is equal to 0 degree or 180 degree. So for a stable equilibrium, the potential energy should be minimum. Are you able to follow? So for a stable equilibrium, potential energy is minimum. So when theta is equal to 0 degree, dipole moment should be parallel to the magnetic field. For unstable equilibrium, it is anti-parallel. That is theta is equal to 180 degree. That is anti-parallel. So M is anti-parallel. We understand the meaning of anti-parallel to be. See here, this is M, this is B. This is the first case. The second case is this is B and M is in this direction. And that is why it is 180 degree. This is 0 degree. Do you understand this? Magnetic moment is anti-parallel to the magnetic field. That is 180 degree. Whereas M and B is equal to what? That is 0. So in this case, this is maximum. U is maximum. Here U is minimum. Okay, don't forget that. So these are the two important cases. Okay.